Right. 244 and 245 were asked. I have some more questions, so I'm going to solve those right now. 244. In 244, it asks us to rewrite each of the following radical expression using fractional exponents instead of radicals. The reason they're introducing this to you now is because Chapter 3, we're going to use exponents and logs, and this will just be helpful for us. So go ahead and look at A. So this right here is written as a radical, because you see the square root, and we want to turn it into a fractional exponent, which is the same thing, it's just written a different way. So how this works, it seems kind of counterintuitive. The squared is going to be on top, so it'll be 5 to the 2 over 3. So the 2 goes on the top, and the 3, the root, goes on the bottom. The reason for this is if you think of like x to the 1/2, this is similar to just the square root of x. There's actually an imaginary 2 right here, and you're taking this to the first power. Okay? So in B, see, to the 5th, this would be 2 to the 5 over 4. Now, I know this looks a bit different. You see the 5 on the outside, and then the 2 on the inside. It doesn't matter because the order of operations, they're kind of inverses of each other. So wherever you're squaring will always go on the top, and then the root goes on the bottom. Okay, so you can think of this as, this is all a power, but you can think of this as the higher power, and this is a root, or your radical. Okay, if you want to think about it that way. Let's see, C, 7, oops, there's no 7, 3. And there's an imaginary 2 here, so it's going to be 7, 3 over 2. D, 7, 3. There's an imaginary 2 here again. You're taking a square root. So this one's 7 to 3 over 2. Same exact thing. And then this one. Alright, then this one, 7 radical 7. You think of this as having a root, so let's do this in parts. 7 times this being to the 1 power, 7 to the 1/2. Then you have common bases. So you know there's imaginary 1 up here, but we can't combine those. We'll need to add them, so we need to get a common denominator. So it's actually going to be 7 to the 2 over 2 times 7 to the 1/2. Now we can combine. We have 2 on top and another 1. We can add them. 7 to the 3 over 2. And then let's look at F. 9, 3, and same thing here. Actually, we maybe can go farther with this. We're actually going to do this. 3 squared to the 3rd, because 3 squared is the same as 9. The reason I did that is I want to find the common base with 3. And then we can rewrite this as 3 to the 1/2, which is the same as the square root. Now we can distribute this. So we get 3 to the 6th times 3 to the 1/2. What's problematic about this one is we need a common denominator for it. So let's see. We need to do 3 to the 12 over 2 times 3 to the 1 over 2, which will give us 3 to the 13 over 2. You know what? That is not right. I made a mistake back here. I was looking at my answer key. Alright, let's go back. I can't distribute this to that one because I think I wrote it down wrong. It's actually 3 squared times 3 to the 1/2. Or the 1/3, excuse me. 1/3. That's where this 3 comes in. Now we can do 3 squared times 3 to the 1/3. Get your common denominator. 3 to the 6 over 3 times 3 to the 1/3. Now we can combine 6 and 1. It's going to make 7. 3 to the 7 over 3. There's your answer on that last one. Okay. All right, so that's 44. Let's look at 45. 245. 245. Solve these special right triangles. All right, let's go ahead and draw this in. X, and 5. Okay, now we haven't really dealt too much with this yet. You learned it in geometry, but I know it's been a while. When you see an X and an X, you mean these sides are congruent, they're equal, so it's an isosceles triangle, which means it's at least since it has a right angle, if this is 90, and the other two angles must be equal, they're both 45. So this is a 45, 45, 90 triangle. Now 45, 45, 90, they have a special relationship. Two of the sides will always be equal to each other. So I'm going to teach you this later, probably second semester, but I'll introduce it now. The ratio for a 45, 45, 90 is this. A, and A radical 2. And this is the ratio of the sides, the length of the sides. So these are across from the 45s. So they correspond. So we're going to make this A, we're going to make this A, and we're going to make our hypotenuse, which is our biggest leg, A over rad 2. Now, we need to solve for one of these equations. We have 3 of them. A equals X, can't solve for. So the only one we can solve for is this guy right here. So we're going to solve for A. So we're going to divide each side by radical 2, radical 2. So it'll give us 5 radical 2 is equal to A. What's problematic about this? You got to get rid of the square root on the bottom, so we multiply by radical 2 over 2, which is the same as 1, and you'll get 5 radical 2 over 2 is equal to A, and since A is equal to X, this answer is also equal to X. So our two sides are 5 radical 2 over 2. Alright, so the idea here is set up your ratios or your 3 equations, 1, 2, and 3, then figure out which one to solve for, and then solve for A. Let's look at B now. B, you don't have a 45 anymore. Now it looks like you have a 30, 60, 90, which is your other special right. So we got 30, X, Y, and 8. So for a 30, 60, 90 triangle, your other special one, the ratio of sides is A rad 3, and 2A. These are just ratios you will memorize. Here's the ratio of sides. So we do the same thing we did in the last one. Now this is going smallest to largest. So your largest side, or your hypotenuse, will be 2A, while your smallest is A. So if we look for our smallest side, X is our smallest, we're going to make that equal to A. Our biggest side is our hypotenuse, which would be 2A. And then Y is A rad 3, the one in the middle. Now if we look at our 3 equations, the only one we can solve for is this one. So we're going to go ahead and solve this equation. This one's a bit easier than the last. 8 equals 2A. Divide each side by 2. A is equal to 4. Great. If A equals 4, what are you going to do with this 4? You're going to plug it back in to both of these. So we know that X equals 4, since A is 4, and we know that Y equals 4 rad 3. And that gives you the solution to both of those. So the key thing here is you got to memorize your ratios, but you'll notice after you memorize the ratios, you label the ratios, and then you solve for A. And the hardest part is knowing which side is which, and we'll get more practice with this, especially second semester. Alright, the last problem that was asked was 56, which I think I checked for homework. So 256, it's a summation. You have 1 over 4 plus 4 over 9 plus 9 over 16 plus dot 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 all the way to 81 over 100 plus 100 over 121. And we need to express this in summation notation. Well, if we got to look for patterns, and the best thing with fractions is look for a pattern on the top and a pattern on the bottom. So when we're actually writing our summation, we're going to have a fraction in it. So if we look at the top first, we notice that 1, 4, 9, there's not increasing by a common difference. It goes up 3, then 5. But it does look like these are perfect squares, 1, 4, 9. So we can represent this as, we'll use the letter I, and let's start with I being 1. So when we plug in 1, you will square it, and you will get 1. 1 squared is 1. 2 squared is 4. 3 squared is 9. And the bottom one, a bit different, 4, 9, and 16, you can't square 1 anymore. It looks like it's almost been moved up 1. Like it's coming earlier. All these numbers are coming earlier. So this actually looks like 2 squared, 3 squared, 4 squared. So if we're still starting with 1 as being I, we actually want to do I, oops, I guess we can write in red, I plus 1 squared. So now we're doing 1 plus 1, which is 2. 2 plus 1, which is 3. Write it in here. 3 plus 1, which is 4. Now we're going to go all the way, and the question is, when do we stop? Well, your last number needs to be 100. So, if our lower bound is 1, what's going to be the square root of 100? You'll get 10. And that's where we stop. We will have 10 terms.